Hi guys, in this video I'll cover the linked list data structure. A linked list consists of nodes. Each node has a value and a pointer to the next node. The linked list has a head pointer that points to the very first node of the list, also named the head node. That node then points to the next node and so on. So we build a list of nodes. Each node stores a value. We can remove values by removing nodes, and we can add values by adding nodes to the list. Optionally, a linked list also has a tail pointer that points to the very last node of the list. That will make it easy to append nodes to the list, because we can jump directly to the last node and add a node at the end of the list without having traversed the entire list starting at the head pointer. Now let's see how this works conceptually. So initially I have a linked list and the head points to null. So this linked list is empty. Now I add 1 to it. So I create a new node. The new node stores the integer value 1. And now I update my head pointer to point to that node. And the next pointer of this node points to null. So in this case, I have a single node which stores the value 1. Now if I add 5 and I start at the head pointer, I check if the head pointer has a next node. This has 1. Then I check the next pointer of this node, which points to 5 in this case. So 5 is the new node that I added. And then this new node has a next pointer that points to null. Now if I add another value, let's say 7, I have to again start at the head pointer. So I always follow the pointers of the nodes. I first traverse to 1, get the next pointer, go to the next node 5. This pointed to null. So if we go back to the previous slide, this was null. So if I want to add a new value, I know I reached the end of the list. I create a new node object and then assign it to the next pointer of the node 5. And so the new node object would store 7, assigned to the next pointer of 5. Now 5 points to the new node 7. If I add another one, again, I start at the beginning of the list. I follow all these pointers. So it would be a loop. Basically, we could have a condition. While the next pointer is not null, I go to the next node. And essentially, I reach null. I create a new node with the value that I want to add, with 4 in this case. And then I assign it to the next pointer of the very last node. And here I add 8, I add 2, and I add 3. What you notice also is that for each add operation, whenever I add a new value, I start at the beginning of the list at the head pointer and traverse the list. So each add operation has to traverse the entire list. So you can see immediately that the runtime performance is big O of n. Now let's see if we want to check if a value is contained. So if I want to check if 1 is contained, I start at the head and I traverse the list to find a particular value. Here I find 1 immediately, it's the head node, so then I return true. If I want to check if 4 is contained, again I start at the head node and I traverse it until I find 4. And if I want to check if 9 is contained, I traverse the entire list. None of these values match, so eventually I reach the end of the list, which is null. I return false. Now, remove operation, there's a tricky case to it. We cannot simply traverse the list and then remove the value. We have to keep track of the previous node of the node that we want to delete, because we delete this node by updating the previous node next pointer. So when we want to delete 4, we have to update the next pointer of 7 to point to 8, basically to skip the node 4. So when we update 7 to 8, next time we traverse it, we get the next pointer, we see it points to 8, and we continue. Here, if I want to delete 3, I simply traverse it, and again, I would have to update the next pointer of 2 to point to null. That way I delete 3. If I want to remove 1, I would have to update the head pointer to point to 5 instead of 1. Let's take a look at the UML diagram. So a linked list consists of 2 classes. On the left, you see the node class. The node class has 2 fields. The first one is the value In this case, I just store ints, so it's a linked list that stores integers. And then I have a second member variable named next. That is a pointer to the following node. I also implement a hasNext utility function. This will simply check if next is null or if it's not null. If it's not null, I know there's a next node following a particular node. So it returns a bool of true or false. On the right side, you see the link class. So it's important when we implement a linked list that we don't expose the internal structure. So we never want to expose the nodes itself. We really just want to have a conceptual interface where we can say we want to add a value or we want to remove a value. In this particular case, we have an integer list. So we can say we want to add an integer at the end, or we want to add an integer at index 3. But internally, this linked list manages all the nodes. So nodes are really kept internal to the linked list. Now, as I mentioned on the previous slide, we have a head pointer that points to the beginning of the linked list. That is the very first node. There's nothing really special about the first node. It's just like a node like any other. It's just the head pointer that is needed to start the list. And then we have functions such as add a value, get a value at a particular index, a contains function to check if a certain value is contained in the list, a function to remove a value from the list, the size function to get the number of values in the list, and we could add another helper function such as isEmpty to simply check if there are any values in the list or if the list is empty. So note that all these functions just operate on the value or on the index. Any code that uses the linked list simply operates on integers. In this case, because I have an integer list. If I were to store strings or any other objects, it will simply operate on strings or on the particular class of objects that the linked list can store. We never expose the node objects. So here you can see the C++ code. I have the node class. I have private member variables. One is integer, since I want to create an integer list. This I just name value, and then I have a pointer to the next node. Note that this is a recursive data structure. So I use an object of the very class that I'm defining here. Then I have public methods. I have a constructor to create a new node with a given value. I have a getter function to return the value stored in the node. And then I have getter and setter function to update the next node. And I have a helper method to check if this member variable is null or not. So does the current node have a next node, yes or no? Now the linked list class has a single private member variable. In this case, it's the head pointer that points to the very first node of the list. I have a constructor, a destructor, and I have some methods that operate on the values that can be stored in the list. So add, get, remove, and to get the size. Now let's see how we can implement this. So here you can see the C++ code. I initially checked if head points to null. If this is the case, I update head to a new node that I'm creating with a given value. And then I'm done. I simply return. Now, if I didn't enter this case and the condition here is false, I know that there is already at least one node in the list. So head is not null. I get the pointer that points to head. I check if this node has a next node. So this internally checks if temp next is not null. If there is a next node, I get the next node and I update my temporary variable. So now temporary stores the address of the next node. Then again, for that node, I check if there's a next node. If there is, I get the next node. So take a look at the bottom here. I have the head node. In this case, I know there is a head node, which is the 1 here. So I get the address of 1. I have a temporary pointer that points to 1. Then with temp.hasNext, I check, does 1 have a next node? Yes, it does, which is 5. Then I say, get the address of next. So get next. This returns the address of next. I update temp to it. So now temp points to the address of 5. So temp points to 5. Then again, the while loop, the condition repeats. So I check, does temp have a next node? Yes, it does, which is 7. get the next node, which is the address of 7, and update temp with it. So now temp points to 7. Then does 7 have a next node? Yes, it's 8. Update temp to 8. Does 8 have a next node? Yes, it's 2. So update temp to point to 2. Does 2 have a next node? True, it is 3. So update temp to 3. Does 3 have a next node? This is now false because it points to null. So we reach the end of the while loop. And now I simply do temp set next. I pass in a new node with a given value. So this creates a new node at the very end of the list. And then I say temp set next. So it updates the next pointer to now point to the new node that I'm creating here. Let's see how contains works. So contains, I want to start at the beginning of the list with the head pointer and traverse the list and then match the value stored in each node of the list. So I use temp get value and compare to my target. So how can we implement this? So here's the C++ implementation. Initially, I get the head node. So this is a temporary pointer that points to the head node. And then I check if temp is not null. I get the value stored in temp compared to the target. If it matches, I found the value, return true. Otherwise, I update temp to the address of the next node. So here again, take a look at the bottom. I have the head pointer. Now, if the list would be empty, head would point to null. So if I assign head to temp, temp would be null. I would enter this condition. So temp would be the null pointer. This is false. I would skip the loop entirely and return false. So it works in the boundary case where head is null. If head is not null, like in this example, let's say we are looking for 7. I get the address of head stored in temp. So temp now points to 1. I check that temp is not null. This is true. I enter the loop. I get the value stored in temp, which is integer 1. I compare it to target. And in this case, like I said, target will be 7. This one is false. I skip the condition. I get temp get next. So this will give me the address of 5. I store it in temp. So temp now points to 5. Then I check the while condition again. I check that temp is not null. This is true. There is a node which stores 5. I get the value of the node, which is 5, compared to 7. This is false, so I skip the condition. I get the address of the next node, which is 7, stored in temp. Now check that temp is not null. This is the case again. I have the node 7. I get the value stored in that node, which is integer 7, compared to my target, which is 7. This matches, and so I return true. If I, let's say, I look for value 9, this would loop until the very end. It basically starts at the beginning until the last node gets the value here, which is 3, compares it to 9, which is false, then gets the address of the next node, which is null pointer, stores it in temp, so temp is now null, and then checks the condition. This is false, so it no longer continues the loop, stops the loop, and then returns false. So it works in the edge case where head is null, it works in the edge case where we didn't find anything, and it works if we find the value anywhere in the linked list. Now the delete operation. So how can we implement delete? Like I said earlier, when we delete, we need to keep track of the previous node of the node that we want to delete. Now let's say we want to delete 8. So 8, we have to traverse the list, but while we're traversing, we have to keep track of the previous node. So initially, I have a temporary pointer that points to the head node, which is 1. And then instead of traversing it, I check if there's a next node, which is 5. And if that node's value matches the target that I want to delete. So I do temp, next, and value. If that matches, then I can operate on temp. So here, let's go over an example. Initially, I have temp initialized to the head node. I did a condition before, so I know that head node exists. I know that the head node is not the value I wanted to delete, so it's another condition. So I have now temporary pointing to 1. I get the next node, which exists, which is 5. Doesn't match the target 8, so I update temp to the next node. So now temp points to 5. Now I check, does 5 have a next node? Yes, it does. give me the value of the next node, which is 7. Does 7 match the target 8? No, it does not. Then I update temp to point to 7. Does 7 have a next node? Yes, it does. This one is 8. Give me the value of the next node, which is 8. Does 8 match the target 8? Yes, it does. So in this case, I found the node that I want to delete. What I do now is update temp.next. So note that temp still points to 7. So temp.next updates the pointer here. And I update pointer to temp.next next. So temp.next next is the 2. So in this case, 7 now points to 2. Before it pointed to 8 and 8 pointed to 2. So by updating it temp.next to temp.next next, I skip 8, I removed 8 from the linked list, and I'm done. Now let's implement this. In the first condition, I check if head points to null. If it does, I return false. There's nothing to delete. Next, I check if the head node's value matches the target. If it does, I store a pointer to the head in this temp variable. Then I update head to head.next so that head points to the node following the current head node. And then I delete temp. This was the head node or the previous head node that I wanted to delete that matched the target. So this frees up the memory. And I return true that there was a match and it was deleted. Next, I create a pointer to point to head. Then I check if the temporary node has a following node. So if temp has next, if there is a next node that follows temp, I get that next node. I call it next. And I check if that next node's value matches the target. So let's take a look at the bottom here. I have head. I create a temporary pointer that points to the head node. So this is the head pointer that points to 1. 1 is the head node. And I create a temporary pointer that also points to 1. This is the line up here. Now I check, does temp, does 1 have a next node? Yes, it does, which is 5. Then with temp get next, I get the 5 node. I store it in the variable next. So next points to 5, temp still points to 1. Now I check if the value stored in the node 5 matches the target. If it does, I enter this special case. So let's say the target is indeed 5. I want to remove 5. Temp set next, and then I pass a next get next. So let's pause a moment and chew on this. Temp points to 1. So temp set next updates the pointer that goes from 1 to 5 currently. So I want to update where this points to. And I want to update this to next get next. Next is pointing to 5. Next get next is 7. So get next gives me the address of 7, and I update the pointer, the outgoing pointer from 1, so that 1 points to 7. Again, temp points to 1, next points to 5, temp set next updates this pointer here to next get next, which is 7. So 7 is assigned to the next pointer of 1. Now I skip 5, but I still have to delete 5 to free up the memory. This is what the next line here, delete next, does. This deletes the actual node. And then I return true that it was successfully deleted. So again, if there is a match, first line updates the pointer to skip the node. The second line deletes the node and frees up the memory. If there's no match, I update temp to temp get next. So let's do another case. Let's say I want to delete 8. First I check if head is null. It's not null. Then I check if the value of head matches the target. It does not. Then I create a temporary pointer to point to 1. I check if 1 has a following node. Yes, it does. It's 5. I create next to point to 5. Check if next matches the target 8. It does not. And then I update temp to temp.next. So temp points to 1. Temp.getNext is 5. And I update temp to 5. Now I check again, does 5 have a next node? 5 does have a next node, which is 7. I create next to point to 7. I get the value in next, which is 7. Check if it matches 8. It does not, so I skip it. And then I update temp to temp.get next. So temp points now to 7. Note that this line I could also write temp equals next, since I have the temporary variable here. So that would be an equivalent. Then I check, does 7 temp have a next node? Yes, it does. It is 8. I get the next node stored in my next pointer. So next points to 8, temp points to 7. I check if the value stored in 8 matches the target 8. Yes, it does. So I enter this block and then I update temp set next. So temp 7 set next, update the pointer to next get next. Next is 8. Get next would give me the address of 2 and I assign it to the next pointer of 7. So now 7 points to 2. The next line I delete next, which is 8, and then I return true. If nothing was found, eventually temp has next would return false. In the case when temp pointed to 3, I stop the loop and I return false, that nothing was found. Now, what is the performance of linked list? We can see that many times in many operations, we traverse the list from the head pointer all the way to the end of the list. At first, if I want to insert something at the very beginning, it would be O1, simply updating the head pointer and then the very head node, the very first node that I just inserted, update the next pointer to the existing head node that was there before. If I want to add something, I would have to traverse the list, so it's ON. If I have a tail pointer, it would be O1. Now, remove would be ON. The worst case here is that the value that I want to delete is stored in the last node of the list. So I would have to traverse the entire list to the very end. I couldn't even use the tail pointer because for the delete operation, I need to update the next pointer of the previous node of the one that I want to delete. So it would work if I have a double linked list where each node points to the next node and to the previous node. But for this basic list, it would be ON. Then contains, worst case, the value I'm looking for is stored in the very last node, so it would be ON. Is empty would be O1. I simply check if the head pointer is null. If I want to clear it, it would be ON because I have to traverse the list and delete all the memory, free up the memory for each node. So I could just update the head pointer to point to null, but then I have a memory leak. I still need to go through and delete all the nodes and free up that memory. And then the size would be ON, traverse the list and count. But this could be optimized. I could always keep an integer as a member variable, increment it if I add a node, and decrement it if I remove a node. So, but most operations perform in ON. When would we use a linked list? Let's see the advantages. So the advantages is that it expands and shrinks as we add or remove elements. So there's no wasted memory. We really just use the memory that is needed to store the elements of a list. There's a small overhead because we have to keep track of pointers for each element that we store. We don't have that in an array list, but we don't have any memory reserved for any values that we currently don't need. And when we do an insert operation or the delete operation, we simply delete the node of the value that we want to delete. So there's no shifting going on like we saw in the array list. The disadvantages are that many operations require ON. So when is a good time to use it? When we want to access the very first element or the last element only. Simply whenever we want to add something at the end, we always do append. It's very easy if we just want to add something at the beginning, and whenever we want to traverse the entire list. So when we iterate over all the elements in the linked list, this is good too. But if we want to have random access, simply get the element at index 5, get the element at index 15. An array list is much more performant. We can jump directly to it. With a linked list, we would have to traverse the list. I hope you enjoyed this video. Thank you for watching.